came up with them based on what you saw within the structure. The way that they're typically classified is based on their interactions with other molecules. So you'll notice that we have a non-polar section, right, which was similar to what you guys had. I believe we've got your classification here, which I believe is actually what you guys were talking about, was the non-polar part. You were looking at just those pieces being present. Right? We've got alkanes, carbon chain, and I don't quite see it there. But what we're looking at is just kind of those aliphatic chains. So their interactions with the rest of the environment is relatively nonpolar because the bonds found in those side chains are carbon to hydrogen, which are all nonpolar covalent, which gives you London dispersion forces. So based on those interactions, we would expect those to be relatively weak. Okay? All of the alkane type chains are usually pretty easy to classify. Where it shifts out of that is when we moved into polar side chains, which then gets a bit dicey. You can see that you've got polar covalent bonds. You've got an OH, you've got an SH, you've got some carbonyls and nitrogens in there. Those polar covalent bonds cause a different type of interaction with their environment. That interaction is so drastically different from the alkanes that we categorize those out as a separate section. Right? So we might say, okay, well that's fine, that makes sense on its own, but then if we shift into maybe the positively charged groups, we still have nitrogens or oxygens. So why do those get categorized differently than the polar ones? It has to do with the reactivity of those. The charged ones end up having acid or base characteristics on top of being polar. That acid and base characteristic changes the chemistry of the amino acid and how it interacts with the environment. That drastic change now separates that out as a separate category. I just happened to look at one that I'm not sure I agree with here. Polar uncharged groups. Take a look at proline in the lower left. What do you guys think? Does that seem to be a reasonable polar structure? No, not really. We're looking at carbons and hydrogens. So even within these categories, you will see debates of what people have classified and where they've put them. Okay, so we have to be kind of careful with that classification scheme because everybody has a slightly different version. I'm pretty sure that if you take a look at what your textbook provides and these charts, you will see some amino acids classified in separate categories. Okay? Depending on where you reference, again, different categories. When it comes to the homework and they're asking you to classify, they tend to pick the ones that are very clearly classified in that, and there is no debate on it. If it comes down to it, and you look at the textbook and you go, I don't know, I would have classified it in that place. Okay? There is a be-all, end-all on what you should be classifying it based on, okay? Particularly for the homework. For an exam, that be-all, end-all is really based off of your textbook. For the homework, they should have a table of how they've classified them within Sapling. So if you open up the hints, okay, or the explanations in the lower left-hand corner, it should give you a link out to a table of all the classifications of the amino acids, which should help you classify according to their system. Theoretically, their system is the same as the textbook. Like I said again, there's some mismatch, and you have to kind of watch out for those. Okay? I can only check those so much because all of those questions are algorithmic, and so when I pull them up, I'll see one set of amino acids. When you pull it up a second time, you see a different set of amino acids. Okay, so I can't check to exclude the ones that aren't categorized the same across the sections. Okay, so you have to be a little bit careful with that. When it comes to the exam, what you'll need to do is be able to classify them as best you can, and as long as you can defend your answer, you're fine. Okay? So your standard categories, you've got your nonpolar, you've got, actually I'm not sure aromatic shows up in your book, but aromatic is one classification. You've got your positively charged groups, which is really just saying that that structure has a base within it. You've got your negatively charged groups, which is saying that that structure had an acid within it. Okay? And then you've got your polar uncharged side chains as well. So you've got these kind of categories. You should be able to classify each of the amino acids roughly to their categories based off the textbook is going to be your best option because you got a nice clean table. It shows it relatively nicely, though unfortunately, depending on the edition, they split it across a front and a back page. Or if you have, it looks like the International Edition, at least split it side-by-side pages so you can look at them. Okay, you can see them both. So be aware of that. You need to be familiar with those. Right. And the classifications that we've got up here are problematic because we're using an older edition textbook, which means I don't have any of the figures in your textbook. Okay? Because it's an older edition textbook, we don't have the instructor resources because they aren't going to release instructor resources for a book they aren't publishing. So I can pick up some figures that happen to show up online that match. Sometimes I can track them down through back channels, but for the most part, the images that show up in the slides will not show up in your textbook because they're different references. Okay?
So, because
Go ahead.
Just comparing this to the book.
Some of them are the same, some of them are different. Okay?
It leaves them out, like in group 1. It leaves out like 3 of them.
Yeah, like you said, proline's in the...
So proline, I disagree with that classification.
It's in,
Yeah, that doesn't make sense to put in a polar group because what's your side chain? It's not polar. Okay, so if you look at a standard reference or a different reference, they probably classify that in the polar. Okay, and this is one of the biggest issues with the amino acid classifications. Okay, is because depending on who's looking at it, they classify it differently. Okay, wherever I pulled this from, decided to classify these according to these categories.
So
Which-
which slide would go with the book?
I would go with the book.
Okay.
Yep.
Yeah, it's like Tyrosine.
Come on, keep going. Okay. This gets us back to the beginning of Chapter 3. All right, so at the beginning of Chapter 3, really what we're trying to do is introduce the concept of our amino acids. Okay, based on the name, you have amino and acid. What does that mean? One of the things that's common across all amino acids is an amino group and a carboxylic acid functional group. Okay, so we've got the amino, which I should show in blue, which we'll talk about in a second, and the acid functional group, which we can show in red. Those two functional groups have some interesting characteristics. So if we scale that out of those nasty looking drawings into this, we should run into the issue that you may or may not remember from second semester organic chemistry, if you were in it. What is that issue? Not tautomerization, that's actually a little bit more complicated. This is just obnoxious. What functional group have I circled? A carboxylic acid. What do acids do? Donate protons. What do they donate protons to? Bases. The amino functional group acts as a base. So right away we have a problem with how our amino acids are typically drawn. One part of the structure is an acid. The other part of the structure is a base. So instantly when we look at our amino acids, this structure should very quickly be redrawn like so. We've got our R group, which I left off. Okay. Why? Because a carboxylic acid is an acid. It's willing to donate that hydrogen to anything that's basic. Well, if we look at the amino acid, it has a base within it. It quickly deprotonates, and our hydrogen changes locations within our structure. Okay. Focus on our charged state. Okay. That's the more important structure for your amino acids. And again, depending on the textbook reference, okay, you should see them always drawn in the charged state, okay, with the amino group positively charged and the acidic group negatively charged. Okay, why? Because at neutral pH, or at most pHs, that's what our structure looks like. Why would we look at neutral pH? biological systems tend to run at neutral pH. So that makes the most sense for our structure, is to be looking at it in that state, not in our completely neutral, no charge state. Okay, which brings up some interesting terminology. When we initially drew it out, it's a neutral structure. Okay? After it does its intermolecular reaction, we end up with what kind of structure? Cancels out. It's still neutral. Okay? But within this neutral structure, it is charged. So we come up with a new term for it. What's that new term?
Charge, not charge.
No, not a bad idea though. Zwitter ion. Zwit, I believe in German, is twin. So what you're looking at is twin ions. It's those ions that cancel each other out to give us an overall neutral structure. So if you hear Zwitter ion as a term, your structure is neutral, but it has charges within it. Okay? Your amino acids are your basic building block for all proteins and peptide chains. Okay? So we've got some chemistry associated with it. Okay? Within our structure, we had that nitrogen, which we said was basic. That nitrogen has another characteristic. Okay? So our base definition is what? Accepts protons. How does it accept protons? What does it need to have? It has to have lone pair. It has to have electrons. Is there another base definition that does not look at protons? A Lewis base, okay, which we could also push out to a nucleophile, is what? An electron donor. So what's the difference between an electron donor and a proton acceptor? They're pretty much the same. The only difference is what they've shared their electrons with. If it shared the electrons with a hydrogen, then it's a Bronsted-Lowry base, or what I would classify just as a base. If it shared those electrons with anything other than hydrogen, it's a nucleophile. Okay, so our nitrogen's a bit tricky. We've got two chemistries associated with it. Okay, and one of those would be that Bronsted-Lowry acid-base chemistry. If we switch over to the carbonyl, we've got some interesting characteristics about that carbon. What is special about that carbon now? So the carbon is sort of involved in resonance because we can look at the electron density being pushed around. Okay, so the negative charge on that oxygen can be scattered across both oxygens. Okay. Let's ignore the negative charge moving. If we just look at that single arrow, what charge builds on that carbon? Positive charge. What kind of a species acts as a positive charge? Careful.
No, acid.
Got to be a little bit careful. So acid is the right idea. Proton donor, H+. That's an acid. But is this H? It's not H+. So it's not an acid. What's the similar thing to an acid? It's our electrophile. Okay. An electron acceptor. Why is this an important distinction to make? Well, one end of the molecule is an electron acceptor. What's the other end of the molecule? An electron donor. This is actually how this molecule can act as a monomer in a polymer. Because I can have one end of that negative interact, or one end of the amino acid act as a negative, and react with another amino acid, but the opposite end, which is positive. I can now link those two to each other. What does that do to the functionality of the amino and the acid functional group? Kind of a more challenging question. So if we take a look at this structure, we've got our amino on this side. Did anything happen to it? Okay, officially it should pick up a hydrogen, so this structure wasn't drawn the nicest. Okay, because at neutral pH it should be positively charged. What happened to the other end that used to be a carboxylic acid? It's not just deprotonated. Take a look back up here. There's our carbon, and we have our carbonyl. We have our carbonyl, carbon to oxygen. We didn't really lose a hydrogen off of that structure. We lost the full OH. Okay. The nitrogen from another amino acid attacks and kicks out the OH. OH is a horrible leaving group. How do you make an OH a better leaving group? Okay, so on one side, we've got our OH that was removed. What happened to the other side? Look at our next amino acid. Say that a little louder. It lost a hydrogen. So if we lose H plus and we lose OH minus, what happened? We lost water. Known as what type of a reaction? All sorts of fun answers on this.
Hydration?
We could look at it as a condensation reaction. Okay, we can look at it as a dehydration because we've lost water from that bond. Okay. If we look at the strict mechanism involved in that, it is technically an addition followed by an elimination. So we have an addition-elimination reaction. Okay. That process now links those two amino acids with each other. And if we further evaluate what we were trying to get at, what happened to the carboxylic acid? Is it any longer a carboxylic acid?
No.
What happened to the amine? Is it any longer an amine? No. We've lost the functionality of the amine and the acid. So if we think back to our amino acids and our classification schemes, should we worry about the amine or the acid? Not very much, because what happens to it once we form the peptide or our protein? It disappears. Those functional groups are no longer present. So I don't care about the reactivity of the amine or the carboxylic acid, because once I put it into the protein, neither of those functional groups exist. Yes, there's an exception. We'll discuss that in a second. Okay? So when we're looking at our peptide chains, we ignore the functionality of those two, because once we're in the peptide chain, we no longer have those functional groups. Once we're in the peptide chain, what functional group do we have? What's the combination of a carbonyl and amine? I'm not sure I actually wrote it there. What was that?
I was going to say amino acids.
No.
Amide.
It's an amide. Okay. So we've now formed what biochemists typically refer to as a peptide bond, which is a bit silly. Really, it's an amide. It's a new functional group. The chemistry of that functional group is drastically different from the starting pieces, which is one of the reasons why it contributes to a lot of our primary, secondary, and tertiary structures. Okay, really just the secondary. Okay. As we continue through the chain, our next amino acid, you'll notice we run into the same issue. Okay, we've lost our carboxylic acid. We've lost a hydrogen off of our amine. We have a new amide bond. Okay? We have a new amide bond all the way through. Questions about what's been discussed so far?
So what disappears again?
The carboxylic acid and the amine functional group. Because what happens, here we had a carboxylic acid.
Right.
Is it a carboxylic acid anymore? No. Here we had an amine. Is it an amine anymore? No. So the chemistry of our carboxylic acid and our amine are meaningless once we've moved into the peptide chain. Because when we're in the peptide chain, do we have those functional groups anymore? They've
So
disappeared and
that's
become an
the
amide.
after-drawn you're saying?
This is after they've
The
reacted.
peptide
This
bond?
is our peptide chain.
So up there is what goes away.
What we've got up top is a single amino acid. When I react that amino acid with other amino acids, it polymerizes in a dehydration reaction. That dehydration reaction results in the loss of the carboxylic acid and the loss of the amine and the formation of a new functional group, the amide. So I no longer care about the reactivity of an acid or the reactivity of an amine, okay, because in the peptide chain, they aren't there, okay, or at least in the backbone. Other questions with it? Oh, I just blanked. Oh, there it is. Sorry, just remembered. I said we don't have to worry about the amine or the acid. Well, is that strictly true? What do we have right here, at the very beginning of our amine or our peptide chain? What was that? Say that louder. I heard it. We have an amine, which should get, well, let's avoid the protonation for the moment. We have an amine with that lone pair. Let's move to the other end of our peptide chain, what do we have? We have a carboxylic acid. So have we strictly lost all chemistry to do with our amine and our acid? No. The beginning and the end of our peptide chain, we still have the amine and the acid. Okay? Because it didn't polymerize. Okay? But any amino acid in the peptide chain, through the middle of it, we've lost the functional group. But both the beginning and the end of our chain, we still have our amine and our acid. So every peptide chain will have at least one amine and one acid, okay, within the backbone. This says nothing about the R groups. Yes?
I mean, looking at it, it looks like it can just keep building on.
So it can continue to build on. So we run into then questions, what controls whether it builds on or not? That's usually enzyme derived. We can go back into transcription, translation. It's translation, right, to go from RNA to proteins. Okay? So our RNA to proteins decides how many amino acids to attach. Okay? One of the things that we addressed here is OH is a very bad leaving group, if you remember from OChem. Okay, well, if it's a bad leaving group, should this nitrogen even attack the carboxylic acid? Well, if it attacks, then I have to kick out a group. If OH never leaves, the nitrogen's a horrible way to attack. There are enzymes that facilitate that attack and allow it to occur, which means in solution, we don't expect that polymerization to happen very easily on its own. It needs to be facilitated. Make sense?
Yeah.
Yes.
Is the length dependent upon if the amine accepts the hydrogen? Like, because earlier you were saying, like, you should always naturally write it, and it's like square ion 4. Should we do the same thing on that regardless?
So if we look at this peptide structure, and we now want to understand something about its structure, we need to understand something about its charge. Okay, if it's charged. Well, is the amine basic? Yes. It should pick up a hydrogen at neutral pH. And I know that neutral pH thing is going to get irritating. It's going to get more irritating when we talk about it in more detail. What happens to the amino or the acid part of it? It's an acid. It should get deprotonated, and it should be drawn with that charge. Okay. If we're saying at neutral pH, our amino acid monomer is this guy. Erase that. Do we have a nucleophilic nitrogen anymore? No. Further, when we look at our electrophilic carbon, we've made it much less electrophilic because there's now more electrons next to it. So an amino acid at neutral pH, is it even willing to go through the reaction? No. So how does it work? There's an enzyme that comes through and helps facilitate the removal of the hydrogen, okay, to activate our nucleophile so that it can then go through and attack. So this is one of the things that I find frustrating with biochem. We look at all the pieces and we say there's no way in hell this works. Oh, biology does it. Thank you very much. Okay. It's cool, it does it. Okay, it's very cool that it can go through and do it. But we look at these reactions, we say there's no way that this should work. But biology comes along, has existed for so long that it's specialized particular enzymes that can then force a reaction to occur when we think there's no reason for it to occur. Okay, which gets tricky. Does that kind of answer your question? It's almost like a dodge, but
Yeah.
there really isn't much of a better way to do it.
Well, I'm just saying, if we have this like on an exam where we're supposed to write something, should we write it in state?
Writing it in the state is what we're going to get into in a little bit, okay? Because that, remember, I keep saying at physiological pH or at neutral pH, and that's because nearly we're always at neutral pH, okay, within biological systems. But can I change that?
Yes.
Yeah. If I change that, does that change the structure? Yes. You're responsible for understanding that change when we change the pH.
But it should be assumed that we're always at neutral pH.
It should be assumed that you're always at neutral pH. Typically, it'll get referenced as physiological pH. Okay, one of the things that I found frustrating, particularly with tables within textbooks, is they will give you the structure of the amino acid, but they won't tell you what pH it's at. Okay? At least they don't make it obvious. They do tell you where the pH is at, in a tiny little size 8 font as a footnote after the figure. Okay? So you have to be very careful with their referencing. Yeah.
So OH being a very bad leaving group, it's still more basic than the amine group, correct? Because I look at it as, yes, I see the reaction that occurs and there's enzymes that are involved, but if that OH was to attack that carbonyl group, pushing the electrons onto the oxygen.
There is no OH. The only way we had our OH is that what we looked at were the pieces that changed. Okay, and that's where we got to be careful with this. We're not getting into a mechanism. We're saying what changed to go from here to here. We lost an OH from this side, and we lost an H from this side.
So it always forms water.
We will always form water.
You're never going to have any OH floating around.
There's no OH floating around. Why? We're at physiological pH. What's the concentration of OH at physiological pH? Okay, you're looking at a relatively neutral environment. If we went through and did peptide synthesis and we had tons of OH floating out there, we'd be at a very basic environment, not neutral. Okay? So the OH that we're referencing, and even the H that we're referencing that's being pulled off here, okay, is just to acknowledge that those pieces exchanged. Okay? And I do find this frustrating within biochem as well, is that what we're looking at is what changed. I don't care how it changed, just did it change? Okay? And when we get into enzyme mechanisms and the details of these individual reactions, we will zoom in and look at an enzyme and say, okay, how is it facilitating these reactions? And that's one of the things that's cool about biochem. In organic, we just have a solution. We throw it in all together. The whole thing has to be maintained all at roughly the same deal. In biochem, you get point changes. So at the exact location in the enzyme where this reaction is occurring, the pH can change drastically. You can go from a pH 14 to a pH 1, okay? Very, very quickly, because at that exact location, the concentrations of H plus and OH minus can vary. The structure facilitates that pH change. Okay? And yes, it's tricky. It's bizarre that it can do it, but that's what biochemistry has as a big advantage. This is one of the reasons why when you move into biochem, if you want to do something, you just say, oh, I'm going to make an enzyme that does it. Find an enzyme that does it close enough, and I'm just going to tell it to do it a whole bunch of times. Okay, so it's kind of neat in that respect. Other questions on this? Okay. Next thing we got to address, if we take a look at that relative structure of our amino acid, okay, our central carbon is a stereocenter. Is that problematic based on what you remember from OChem? Yeah, you all loved OChem and chirality and all that fun stuff when you had to predict the stereochemistry of each of your products. That becomes really, really important to figuring out the answer. Well, if our amino acids, our basic building blocks, have stereocenters in them, if I change that from being R to S, does that change how that molecule interacts with every other molecule?
Yes.
Yeah, it has a massive effect on it. Okay? Well, it turns out that our amino acids are only one configuration. And I always get it backwards because it always switches around. I think our amino acids are D or L. It's a D. Okay. They're mainly your D amino acids, which is fun because if you remember from organic, what was our definition from chirality?
Right turn.
R and S. If you keep pushing that further into everybody's least favorite subject beyond chirality is optical activity. And optical activity, how do we define it? Plus and minus. You see levorotatory and dextrorotatory. That's D and L. That's lowercase d and L. When we're talking about D and L with respect to amino acids, it's capital D, capital L. Is that different from all of those other systems? Yes. Okay? So you have an entirely new system to worry about when trying to determine these D and L situations. So we've got a lot of chirality popping up within our molecules. So they kind of invented the D and L system to make it quote unquote easier to interpret. Okay? So it's a new set of rules, and those new set of rules are different than what you would get from organic. Okay? So since all of your molecules are chiral, okay, there was a new situation. It really drove with carbohydrates, not with our amino acids, but our amino acids are a good place to bring it up, is that we have so many different chiral atoms in it that we change our viewpoint on the molecule to hopefully remove all of these wedges and dashes. So what I've gone through and done is I've taken our amino acid and I've changed the orientation of the molecule. Okay. So if we take a look at that top structure, we've got our carbon, whoops, in the middle that has 1, 2, 3, and I shouldn't be drawing a dashed, hydrogen, 4 groups around it. So that carbon is tetrahedral. Okay, so this guy Fisher came along and he said, I don't want to deal with these wedges and dashes, so I'm going to change how I view the molecule so that I can simplify my structure. So what he went through and did was he took the structure and he rotated it so that the acid is aimed away. Okay, so in our current viewpoint, it's not aimed away, it's in the plane of the board. So he took that molecule and he rotated it. Okay, so we're going to attempt to do something here. It's going to look really goofy, but it works. Okay, so left leg, right leg, amine. Right leg's the amine, left leg's the acid, right? Matches the image up there. Okay, and I'm going to take my arms. We're going to call our group, and I'm going to switch it the other way. Oh, I can't switch it the other way. Damn it. Okay, so we got our R group and we got our hydrogen aimed away. So there's our standard tetrahedral structure. So we got a wedge and we got a dash. Okay. Didn't like that viewpoint, so he changed the orientation of the molecule. Okay, the way that he changed the orientation of the molecule, well, it's not going to work that way. I'm going to have to do it this way. So we got this view, and he went through and changed it now, so that what he ends up looking at instead is that, which means no atom is in the plane. We've got 2 atoms coming at you, my hands, and 2 atoms going away, legs. Right? That's our Fisher projection. He's changing it so that it looks in this really goofy kind of position. He then further changes it so that the carbon backbone, okay, why the carbon backbone? Organic chemistry is all about carbons. Biochem is all about carbons. Put the carbon backbone on the vertical axis. And he aligns that backbone according to priorities. The highest priority carbon is at the top. The lowest priority carbon is at the bottom. Okay? So there's 2 ways that we could look at that, depending on which chiral atom we were looking at, be it R or S. Okay? He then looked at that structure and said, okay, that's a nice way to look at it, but I got all these wedges and dashes. But if I always take the highest priority carbon, and I put that at top, and I make sure my carbon chain runs vertical, and then I make sure, even further, always, if I have more carbon atoms that I need to include, they are always oriented away, I can change the viewpoint of that structure. Shucks, I didn't actually draw it. It's probably because I can draw it easily. What I end up switching this to, then, becomes this structure. I now have COOH. There's my R group, H, and H2. No more wedges and dashes. I can use solid lines all the way through it. Because as long as I am in the Fisher projection, by definition, I have this alignment. The wedges and dashes become implied. If we move to the other structure, same deal. Okay. And if we go through and deal with this, there is no way that I can get these 2 structures to superimpose on each other because of, again, the implied wedges and dashes. Okay. Which then brings up the next point. Look at our chiral atom. Okay, we'll ignore the carbons. We're only going to look at what we could refer to as the bow ties, okay, the atoms to the side. Which is higher priority? NH2. Why? Why is nitrogen higher priority than hydrogen? Atomic, I don't remember. I'm pretty sure it's mass. Okay. Its atomic mass is bigger, which means it is a higher priority. Okay. If we look at the other structure, again, nitrogens are higher priority. Where's the nitrogen in our first structure? The left side of the structure. So we call that L. Move to our other amino acid. Where's the nitrogen? On the right side of the structure. We call that D. Those are capital letters. They are in reference to, officially, the second to last chiral atom within your structure. When we're looking, yeah, it's going to become really messy when you look at carbohydrates. When we're looking at amino acids, we're only referring to that carbon, okay, which is known as our alpha carbon. Okay, so the carbon that's our stereo center. Okay? That's where our D and L come from. Where is that amino group located? Why the amino group? Because it's higher in priority. So some of the rules overlap, some of them don't, which makes it even worse. Okay? Why do we not use the system of plus minus, lowercase d, lowercase l, or RNS? The reason this D and L really came about was to simplify our assignment for each of the carbohydrates. Right? And that's why we look to it's actually the last chiral atom within our structure, not our second to last. Okay, our last. I think it's our last. In this case, we only have one. Okay, but what we're looking at is the location of our highest priority group around that particular chiral atom. And for some reason, they decided that that made it easier to interpret chirality within the individual molecules. Because you can change the chemistry around that one position, you can switch it from a D to an L. Okay, but if we change the stereochemistry around any of the other positions, how do we fix that? We give it a different name. Okay. Kind of.
I was just curious, you were saying that they did it because of carbohydrates. Is that because you're looking at only hydrogens and OH groups and they're rotating?
It's not just hydrogens and OH groups. That's not the issue.
Well,
That's the
sugar,
result.
sugar.
That's here. The issue with our carbohydrates is it's not one chiral atom. It's like 5 or 6.
Yeah, depending on the chain.
Depending on the length of the chain. So we needed some way to simplify those. So we picked one chiral atom to simplify it based off of, and then we changed the name for every other misorientation or misalignment. Because otherwise you have to go through with a carbon structure of 6 different chiral atoms, and every single chiral atom is a different RRS. You have to then label each of those RNS all the way through. So that's a lot of work. If we go through and just, why I love biochem, memorize what the structure is, then you don't have to deal with RNS. You just memorize a name. Oh, that's erythrose, not glucose. Awesome. So you end up having to deal with, now instead of being just 20 amino acids, you get something like 60 carbohydrates. All of them with slight variations of their names. Okay? So D and L, capital D and L, are in reference to that chiral atom and where your highest priority group is located. Plus minus, lowercase d and l, are looking at optical activity. RNS is the absolute configuration of where the atoms are relative to each other within an individual structure. All of them get to the same point. They have very different rules about how you name it. Okay? So for this class, pushed to you're in the Fisher projection, capital D, capital L. You need to know those rules. Kind of, sort of? Okay. Yeah, I know. I'm not happy about it either. I will also complain about this. Your textbook does a horrible job referencing the dashes. Okay? These two dashes mean very different things. Okay? They are not the same thing. Your textbook uses them interchangeably. Okay? Very, very irritating. You will also, and this is not just your textbook, this is all biochemists. Okay? Interchange these. And I've noticed some organic chemists interchange them as well. This is why when you look at my structures, when I do dashes and wedges, when I hand draw them, if I'm going to show the dash or the wedge, that's kind of clear. And if you show the dash, you'll notice all of my lines are the exact same. Because I don't want to bring in this confusion of what the tapered dash means. The tapered dash means that this carbon is in front of that nitrogen. If we now swap it here, what does that dash mean? The nitrogen is in front. Does that change the stereochemistry? Massively. Okay? So be aware of that issue. The textbook uses them kind of interchangeably and always to mean the same thing, that atom is just going away. Which atom? Good question. Okay? So be a little bit careful around seeing those dashes. I just want to make sure you're aware of that issue. Okay, so we've got all of our amino acids. You've got the names, the 3-letter code, the 1-letter code. I want you to memorize 5. So for exam 1, I will ask you for some number of amino acids. You need to provide the name, 3-letter code, and 1-letter code. For any other biochemistry class, they should tell you to memorize all 20. Okay? Because you need to know what they are to be able to predict something about their chemistry further on down the line. Okay? The next thing that I'll ask you to memorize on top of it is something about their chemistry. Okay? The chemistry being the structure of your functional group. Does that act as a hydrophobic structure because it's nonpolar? Okay? Does it act hydrophilic because it is polar? Understanding something about that secondary chemistry becomes really, really important when we move into understanding how proteins fold. So you need to know something about that structure and how you classify it. That classification system is fine if you base it off of the textbook. Okay? Questions about that?
Do we need to know how to draw the structure?
Well, if you've memorized, oh, so yes, you do need, straight up, you need the structure, yeah. Okay?
Which 5 do you want us to know?
Any 5 you want, any 5 you want.
Structures?
Yep.
Structure, name, 3-letter code, 1-letter
Structure,
code,
name,
chemistry.
3-letter code, 1-letter code, and then its classification. If you've got the structure, you should have its classification. Okay, that's why we spent some time talking about bonds and forces at the beginning of the semester. Because once you have a structure, you can then predict what its intermolecular forces will be and how it will interact with other species.
But it's gotta be one of the definitions from the textbook, not one of ours.
By one of yours, don't use anything that you've written up on the board. I won't accept those. If you use a classification from some other reference you found, I'm fine with that. Just realize you may have to defend your answer. So if you've gone through and, for instance, if you used, oops, it's this direction. If you had memorized off of this table and put proline as polar, okay, I would probably have marked you wrong, but then when you get your test back, you come back and say, hey, here's the reference. Straight out of your slides. You said it was polar. I go, oh crap, I'm right. Or not, I'm right, you're right. And I'd give you the points. Okay?
Because according to the book, it's not polar.
Yeah. According to me, it's not polar. It doesn't make sense to put it there.
Oh, yeah, it's not
Yeah.
polar. That's why I was like, proline.
Yeah. Yeah, you definitely run into weird issues. Probably the reason why it's classified as polar due to its effect on the protein secondary structure and tertiary structure. Okay. So the next issue that we run into, which we've already started to address, is this acid-base characteristics of our amino acids. I can't remember if I actually put figures on this or not. I did. Yes.
So,
Where are we
back with
looking?
the D and the L,
Uh-huh.
the polypeptide chains
Mm-hmm.
are most often the proteins are polypeptides,
Yes.
and they're always L.
Like I said, there's a lot of memorization, and this is one thing I tend to not memorize very well. Your amino
That's what
acids,
it says in the book.
it's L, so then there it is. So your amino acids are always L.
Right.
Yeah.
So that's why when you were describing it, it was like, well, the L and the E really are only for the smaller peptide chains.
Well, L and D are possibles. So if we look at, we go back to the origins of life. If you have equal probability to get L and D, we would expect that at this point in life, what would we see within our proteins? An equal amount of L and D.
Yes.
We don't, which means there was a clear preference for one over the other. That preference does not exist in any of our understanding for organic chemistry.
Right.
Okay? Which then makes it a challenge for anybody trying to discuss the origins of life happening naturally, because there is no fundamental reason why you should have one over the other, but we very clearly have one. Okay? Some of that can come from quartz. Quartz has a handedness associated with it, and you could make an argument that there was a pocket of quartz where life first started. That life had a jump start and was able to dominate and kill everything else that came after it. Okay. So the whole origin story is a whole separate can of worms, but that's one of the issues that pops up is why do we have only one version for those?
I thought you said amino acids are D, but I guess.
I don't remember. Like I said, it's one of the things I just don't.
Either or, right? Because it
It can be either or, but in life, we only form one. That
It's the same,
one,
But it's also the same with carbohydrates. I mean, it's very
Yep.
similar, is
But it's
both
the
exist, but
yeah.
one is preferred.
one is preferred.
And
So if you think about scissors, right? Are you right or left-handed? Okay, it doesn't work as well. Anybody left-handed? Oh,
my
well,
husband is.
that ruins the point of this. Okay, if you look at right versus left-handed scissors, you'll notice left-handed people hated elementary school with cutting things because everybody had right-handed scissors. And if you try and use right-handed scissors when you're left-handed, it really doesn't feel comfortable. And that's because the scissors are chiral. They're built to a right hand, because odds are most people are right-handed. Okay? Same thing is going to happen in biology. Your enzymes are all a pair of scissors that can only cut one particular handedness of molecule or interact with that. So if we look at a system where we have both possibly showing up, you can have a D amino acid and an L amino acid, and your enzyme would only be able to react with one. So once we've built that preference, we can't reverse it because the enzymes have designed themselves in such a way to only interact with it in that particular fashion. So can we get a verdict on that? Is it L or D for your amino acids? It's L. Okay. Your amino acids, the book is right on that. Yeah. That's just one of those facts things. It's not an interpretation. So facts things it does very well.
So is L kind of like saying it's S, or?
No. No. Don't touch it. Don't touch it.
Yeah.
L means that your amino is on the left-hand side in your Fisher projection.
Okay.
That's it.
In protein.
In proteins.
Yeah.
If your highest priority group is on the left-hand side, it is L, period.
Yeah.
Right.
Right? If you move to sugars, if it's on the left-hand side, it's still L.
Yeah.
Okay? But in sugars, it's
But
most
it's
commonly
D. It is most commonly
D.
Yeah.
Right.
Okay? So you do see switches in the chirality, but it stays fairly consistent within that vein. So carbohydrates tend to all be D. This is one of the reasons why I get it backwards all the time. And amino acids are L.
Yeah.
What about if your R chain has the highest priority than the amino?
Fisher projections, the carbon chain always goes vertical. Always. There is no exception.
You only consider the horizontal one, the amino and then the hydrogen.
Yep, you're only concerned about the amino and the hydrogen on the left and right for the structure. But they will never be on the vertical axis. Just because your book randomly mentions this one, we'll start real quickly, because you all memorized the structures already. I memorized the structures already, I hope. Glycine, D or L. You can cheat and look at the structures, because I may need to change my answer for my question.
It's, well, it's,
But they all have amino.
Where's glycine? No, I got it right. Glycine, D or L. Anybody seeing a problem with calling this D or L?
there's a carbon. It could be.
It's not a stereo center. We can't assign D or L to it. D and L only apply to stereo centers. Okay? So it is a trick question. Okay, glycine is the one amino acid that doesn't have a D or L preference because it doesn't have a stereo center. Because your side chain is hydrogen. Okay? So this can be one of the reasons why it's helpful to know the structures, because you can come up with some of this interpretation.
Are they all automatically drawn in a Fisher projection when you look at it, or do we have to do a Fisher projection?
It would be nice if we were consistent with how we drew things. We're not. So sometimes they're drawn in the Fisher projection, sometimes they're not. If you see this kind of cross formation, that's Fisher. Anytime that pops up, that is Fisher. Every single time. But it does not mean that if it's drawn any other way that it's in a Fisher projection. Okay. Did that. Okay, so this gets back to the question that a few of you were kind of alluding to when we were looking at the chemistry of these. What happens if we change the pH? Okay, well, at really low pH, what can you tell me about anything at low pH? What does that mean? It's acidic. Man, I should have put on a belt today. There's a lot of hydrogen ions present. Okay, so at low pH, we've got all of our hydrogens added to our structure because we're at such a low pH that by definition, we're so acidic that all the functional groups within our amino acid will act as bases. So you'll notice the acid functional group has a hydrogen attached to it. The amino group has a hydrogen attached to it. What happens if we now push this all the way to the extreme and go to a wicked high pH? So now it's really, really basic. Okay, well, if we add a base to our acid functional group, what happens? Removes the hydrogen. That makes sense. What happens to the amino group? It loses a hydrogen. Okay? So the frame of reference that I always go through with all of the amino acids, particularly in this sequence, is I draw out the structures. And I start at wicked high low pH, put all the hydrogens on my structure. Then I look at the extreme, at wicked high pH, and I remove the hydrogens. You'll notice that in the case of the acid functional group, it becomes charged. It becomes negatively charged. What happens to the amine functional group? Becomes neutral. Why do I not remove another hydrogen?
You can't add two negatives.
No.
Since we're not dealing with pKa's that high.
You're not getting to an environment that is basic enough to remove that hydrogen. The pKa, and this is also obnoxious when it comes to amines. If you look up the pKa for an amine, they almost always tell you 9, which is disingenuous. What they're telling you is the pKa of the acid form of the amine. The acid form of the amine is not NH2, it's NH3. Okay? What's the pKa for real for an amine, where the amine acts as an acid? 26, 27. Okay? Very, very weak acid. Okay? So that hydrogen is not easy to remove, particularly at biological pH systems, okay? Between that 0 and 14 range. Okay? In organic, we can do whatever we want. Biochem, we cannot. Okay? We're stuck within the pH range because everything we do is in water. Okay? So now what happens as we adjust the pH? As we go from, I personally think easier from the acid side, so that's where I'm going to start. I now start to add what to get the pH higher? Base. Eventually, what's going to happen to this structure?
The acid's going to deprotonate.
I'm going to have to deprotonate. I'm going to have to remove a hydrogen. Which hydrogen? Okay, I'll kind of accept that. Why the carboxylic hydrogen? It's weaker because
That's what I know. I was going to say nitrogen.
the carboxylic acid is a stronger acid. How do we know it's stronger? I wish we had some way to qualify the strength of an acid. Oh, perhaps the pKa. The pKa of your carboxylic acid is roughly 2. The pKa of the amine is roughly 9, which means which one's more acidic? The carboxylic acid. So as I slowly add base into this, the acid is going to be the first one to react. And I will reach a point where I've added enough base to react with all of the acid, which means my structure now becomes, did I stepwise this nicely? I did not. Whoops. I get rid of the H off of my carboxylic, that one. And I would still have the hydrogen on my nitrogen. Okay. What is special about this species?
It's neutral.
It's neutral. Okay, this is my neutral, and I'm just going to call it Zwit, Zwitter ion species. What was my charge to begin with at low pH? Positive. What was my charge at the end? Negative. Okay. This neutral state is kind of neat. Okay, because we have really no charge overall for the molecule. So one of the typical classifications for amino acids is, when does that happen? Okay, well, that happens at the exact point that you are halfway between this point and this point. Well, if you pull out a titration curve, that exact halfway point is the average of those pKa's. So if I take the pKa1 being 2 and the pKa2 being 9, if I now take the average of those two, I know the pH for my neutral state, okay, which in this case is 6 something? 5.8? Okay. I don't know. 2 plus 9, 11. Yeah, you're right. That was a bit silly. Somewhere about 5.5, 5.8. Okay. This point is so important that we give it a new name.
Speak there, because sometimes that math stuff confuses me.
Oh, it gets worse.
Yeah,
Yes.
I know, but if I were finding the middle point, 9 minus 2 is 7, it's 3.5, so I just add 3.5 to 2, right? Because when you all went to 11, that just confused me.
Average,
Okay,
2
so
plus
yeah.
9 is 11
Got it.
divided by 2. So yeah, you did it a different way to come up with it.
Yeah.
This point is so important, it gets referred to as a new thing. It gets called the PI. All of your amino acids will have reference to this PI. That I stands for the isoelectric point. Okay? The point at which your structure is an overall neutral charge. Okay? I for isoelectric, which you may remember from 151 way long ago when it was equal to some other atom, the point at which your electron configuration was the same as a different atom. So your isoelectric point for amino acids is when they're all neutral, okay, 0 charge. Okay. Would we expect all amino acids to have the same PI? Why not?
Different molecules make it a different charges.
Well, but don't they all have an amine functional group?
Yeah.
Aren't the amines all roughly the same pKa?
But there's other groups.
The R groups can get in the way and adjust your PI, which makes this more complex because now we have to find the point at which you are isoelectric. It's the average, okay, of the pKa's around the isoelectric point. So the point at which your structure is neutral. If your R group is acidic, you're going to be using different pKa's than if it was basic. Your textbook comes up with some way that makes no sense to me whatsoever to calculate the isoelectric with your 3 pKa structures. Okay, the way I recommend doing it, which is everybody's least favorite way to do it, but this is how it works consistently. Draw the structures. Okay? Draw all of the structures along that pH scale from wicked low pH to wicked high pH. As you go through, you will start to remove a hydrogen. When you remove a hydrogen, that is going to change the charge of the structure. Find the structure where your overall charge is 0. Once you've found that structure, look at the pKa's to either side, average those two. All right, yes, we will do this again when we have an actual example. All right? We're just kind of out of
So you
time.
just draw the structures like the Fisher structure?
And actually, it doesn't matter. Because the only reason we need the Fisher structure is if we want to know some information about chirality. We don't need to know any information about the chirality. We want to know something about the functional group chemistry. So as long as we can see it, you're fine. Okay? So remember when we were talking about acids and bases and titration curves? Let's see if it shows up on this next slide. I actually called it the Zwitter Island. What we're going to end up doing with the next few slides. Number 1, we're going to look at tyrosine. Okay, so what I would recommend you do before Thursday, look at the structures for tyrosine on this low pH to high pH. Draw them all out. Put the pKa's over your reaction arrows. Try and solve for what you think the PI is. Okay? And then I will go through and solve that with you guys on Thursday. We will then take that same tyrosine example with the reaction and look what we're going to have to draw here.
Yes, a titration.
A titration curve. So that same titration curve that we loved last week, you're doing again, but in a very particular situation. You are now looking at the titration curve for tyrosine. Okay. That is darn close to the end of chapter 3. Like I said, we've got some details on the PI, which we'll talk about. You'll notice that we've got a big list of PIs for all of your different amino acids. This figure I don't like quite as nicely as your textbook, because your textbook actually groups the amino acids that all have a third pKa. Okay, whereas this one has them scattered, alphabetically? Yeah. After the PI, we've got some basics of our amino acids. We've got a peptide bond. Okay? And then what we should be doing would be moving into chapter 4. I just posted chapter 4 slides. Almost undoubtedly, we are not going to get all the way through chapter 4 before exam